So section 14.7, we talk about the reaction quotient. And first thing you think when you see the word reaction quotient usually is nothing, right? You see that, it means nothing to you. I'm guessing, right? I'm teaching to the kind of student that I was. So I saw reaction quotient, it meant nothing to me. So I get a little further into the section and I find that quotient, watch this now, the reaction quotient is given as a concentration of the products over the concentration of the reactants. Yes, let me say that again. The Q, the reaction quotient, is given as the concentration of the products over the concentration of the reactants. Some of you are thinking and looking at that and saying, wait a second. We've just spent 4, 5, 6 sections talking about something that looks a lot like that, but we called it something different, right? So let me go back and remind you. The law of mass action says that if A moles of A plus B moles of B is in equilibrium with C moles of C plus D moles of D, did you hear what I said? It's equilibrium with. The equilibrium constant is given as the concentration of C raised to the C, concentration of D raised to the D, over the concentration of A raised to the A, and the concentration of B raised to the B. Which is exactly what we're talking about here, right? Except, here's the big difference now. We said this was at equilibrium. At equilibrium. Okay. What that means is we could possibly consider this system at some time other than equilibrium, and you still have concentrations of products and reactants, right? But they're not necessarily K. Okay? Right? So if at some time and it's not at equilibrium, we would call that Q something else. What would you call it? We would call it the reaction quotient. The reaction quotient at some system, at some time, which is not necessarily at equilibrium. So the first thing I would say here to you is a very good news. The reaction quotient Q has exactly the same form as K. By the way, for this reaction, this would be the concentration of C raised to the C, concentration of D raised to the D, concentration of A raised to the A, and concentration of B raised to the B. And I would say, watch this now, not necessarily at equilibrium. Could be. This is at any time. Okay? And this is only if the system is at equilibrium. All right, so that said, let's think about this. Suppose that we have a K and a Q that are given here. If Q is equal to the concentration of the products, how do you spell products? With a C? No, with a U? Okay, there you go. Products over reactants. And if Q is 0.55, and we know that equilibrium is supposed to be 1.45, which is bigger. Well, it looks like 1.45, well, of course, 1.45 is bigger, and that means that at Q, I don't have enough products. If Q is too small, and what I mean by that is if it's smaller than K, then I don't have enough product, right? Okay, you see that? And so what that means is that things are going to go toward the products. Okay? Now, what if I have 2.55? That means my numerator's too big. It means I have too much products. That means it's going to go away from the products or toward the reactants. Okay? And if Q is the same, then it means I have just the right amount of products. And when I say just the right, of course, I'm assuming that I want equilibrium. That's something to be desired. And of course, systems that we're talking about, we're typically talking equilibrium as if it's the end goal. Okay? So if Q is equal to K, that means that my products and reactants have just the right amounts in order to be at equilibrium. Okay, so let's think about this now in the simplest terms. If Q is less than K, that means my numerator with my products is too small. And in the textbook, Tro, everybody else is also going to say this means that the reaction goes to the right. Right? It goes in that direction. It gives more products. Okay? If Q is equal to K, that means the numerator is just right. The reaction, can you read my writing? Is at equilibrium. Okay? And if Q is greater than K, that means that the too much product. That means that the reaction will go to the left. It's going to go that way and give less products and more reactants. Okay, that's what this means here. And if you're thinking about this in terms of on a quiz or exam, just write out the expression products over reactants. I know I misspelled that. I'm leaving letters out here. Concentration of products over the concentration of reactants. Write that out. And that will help you sort of think about this. That means that Q is too big, products are too much. We're going to be going in that direction. Okay? All right, I think we have a practice problem here now. Consider the reaction and its equilibrium constant, 81.9. Okay, so we have K is equal to 81.9. A reaction mixture contains a partial pressure of iodine, 0.114 atmospheres, partial pressure of chlorine, and such, okay? Is the reaction at equilibrium or not? Okay, so we're going to say the reaction quotient is going to be ICL. Oh, these are partial pressures. This is, we're going to be using KP, not KC. So the partial pressure of ICL squared is the partial pressure of ICL squared. Has exactly the same form as equilibrium, constant in terms of concentrations. Exactly the same form. Pi2, PCl2, right? And so PICL 0.355 squared over Pi2 0.114 0.102. Get my calculator out and do this. You should do the same. Fight the temptation to sit back and passively take this stuff in. 0.355 squared divided by 0.114 divided by 0.102 equals 10.838. 10.838. Can you read my writing? If Q is 10.838, Q, it looks like it's less than K. All right? So if Q is 10.838, at equilibrium it's going to be 81. That means my products are not big enough, right? It's too small. That means I need more, okay, in order to go to equilibrium. So is the reaction mixture at equilibrium? No. The reaction mixture is not at equilibrium. If not, in which direction will the reaction proceed? Well, K is bigger, and so we're going to need more products. Reaction will proceed right or toward the products. Okay? All right, is that helpful? I think that's the only example we have for this section, so I think that's it.